Hello, everybody. It's a pleasure being here. Thank you to the organizers for giving me the opportunity, and thank you all for your patience as we do a tag team lecture, James and I. As you may have noticed, we have our 3-month-old baby here with us, so this has been a convenient way for us to still be here and participate, and yeah, you get 2 different perspectives on the same material. So I'm hoping to carry on where James left off. I hope, as I do this, that you guys will ask lots of questions. I know in this type of auditorium, it's sometimes a little intimidating to raise your hand and say, wait, I have no idea what you just said about whatever. But of course, while everyone here is rapidly becoming an expert in something, not everyone is an expert in all things. So please ask questions as they come up. Let's see if I can make this board go up just a bit. Oh, wrong one. OK, so last time, and do let me know if I need to write bigger as well. What you were exploring with James, he was starting with 10D Sugra plus Yang-Mills. In the process of compactification, he was reducing to lower dimensional theories and setting up for you some of the features of what you can get and how you solve the problem of what is possible from string compactifications. So specifically, we were looking at things, not exclusively because he talked about domain walls and things, but we're looking at solutions that could include 4-dimensional Minkowski space, that's us, across some compact space that we're integrating the 10D theory over in order to get rid of all those degrees of freedom, and then being left with a 4D Yang-Mills theory coupled to supergravity. So last time he was showing you the equations of motion, various solutions to those equations of motion. The one that I want to begin with, so the Strominger solution to heterotic theory. He mentioned the torsion solutions. The most general torsion solutions for heterotic Minkowski vacua are the following. So if you look back at your notes, the torsion classes that he wrote down, if you have this combination, so 2 of them equal to 0, 2 of them related, and including relation to the dilaton, and 1 free, this will solve the so-called Strominger solution. This is the most general solution to the heterotic string that will preserve Minkowski in 4D. I should say, by the way, that the reason that we're focusing on heterotic, although of course heterotic is interesting, is that this is a really good arena to very simply illustrate a lot of the tools that are general for much broader classes of string compactifications. So this is why I'm illustrating it here. You can go a very long way and state things very concisely. So if we have this, then we get R13. But we haven't quite finished with the equations of motion. So where James left off, he was talking about the data of the compact space, X6. He was not talking yet about the gauge fields. So that's where I want to begin today. So what about A mu? What do we do with those guys? And the answer is that they also have to satisfy equations of motion, of course. So we have, for example, a Bianchi identity, which relates the 3 form of heterotic to a combination of the curvature and the field strength. So this is the 3 form from 10D curvature over, this has to be satisfied in the full 10D theory, but in our case, we're looking at this over the compact space, X6. This relates trace squared of curvature to trace squared of gauge field strength. And if you integrate this over 4 cycles, so this is for anomaly cancellation, and it's the so-called Bianchi identity. And if you integrate this over 4 cycles, this implies that geometrically, churn 2 of the holomorphic, or even real tangent bundle, is equal to churn 2 of the gauge bundle. I haven't told you anything about bundles yet, so this is just an aside comment. We'll come back to what that actually means, but this is a statement about topology of the space and gauge fields. We'll return to that in a second. So this is one condition that we need for the gauge fields. Another condition is what happens from the equations of motion. So So the gaugino variation in terms of real coordinates gives you the following equation, which I'm going to solve in a simplified case. So I'm going to look at the Strominger solution. Here, these two conditions actually have a strong geometric meaning, the vanishing of these two torsion classes. This is the statement that you have a complex manifold. So with the solution I'm considering, if x6 is complex, I'm really going to write that as x3, and I'm going to introduce a, b, and their bars, running 1 to 3 rather than 1 to 6. And in terms of those coordinates, I can rewrite this equation as the following. In terms of the 3 form and 2 form that James introduced last time, these equations have to be true. So these are the conditions on the gauge field relating it to both the Hermitian form and the 3 form. You will be forgiven if these equations do not look terribly obvious and or useful. What am I supposed to do with those? In general, these are very nonlinear PDEs in terms of the gauge connection in the background, and they're hard to solve. So I'm going to simplify it a little still further. So simplify. And we're going to assume that dj is 0. This condition, if the Hermitian form is closed, this is the statement that the space is, quote, Kähler, which means, among other things, that the metric takes a very simple form. The metric GAB bar, the 1, 1 component of the metric, looks like 2 partial derivatives of something. So this is what it means to be Kähler. And in the case of the Strominger solution, if you have a Kähler solution, that implies that x3 is a Calabi-Yau threefold. So I'm going to reduce to the Calabi-Yau case now to talk about gauge fields. OK, so here, do I have space? No, probably not. Let's see. Kind of tricky to figure out. Oh, no, that one goes down. And then I want this one down a bit. OK, you can still sort of see that one. So here the equations of motion reduce still further for the gauge field. And now they become a little bit easier to write down. They look like this. The statement is that over the Calabi-Yau background, the gauge fields have to satisfy 2 conditions. This guy is actually very easy to state in terms of the background gauge fields. This is the statement that the gauge fields are, quote, holomorphic. Which means that the transition functions that patch together the gauge degrees of freedom over the compact manifold are all holomorphic functions. So that's not so bad. That's easy to understand. This guy is pretty horrible. This is actually 1-to-1 with the property of what's called bundle stability. We're going to come back to this too, but I'll just mention it now. And in general, this is hard. This is a nonlinear PDE that you have to solve for a metric that you don't know and a gauge field strength that you don't know. So this is pretty nasty. But if you have a Calabi-Yau background, there's at least one class of solutions that will always give you a solution to Strominger's system. So we can always solve the Strominger system. Because one choice that I can always make for the Calabi-Yau case that will solve all these equations is I can take the spin connection of the manifold and set it equal to the gauge connection of the Yang-Mills theory. If you make this choice, these equations are automatic. So this reduces essentially to Ricci flatness of the manifold. As James mentioned last time, X being Calabi-Yau. This is Ricci flat Kähler. So here, all equations of motion will be satisfied, and the Bianchi identity that I've hidden on that board, oh, here it is right here, if you can see it, this DH condition that I write down, this will be automatically satisfied. The right-hand side will be canceling, and H equals 0 in vacuum. So this is a completely fluxless solution. Yeah? I'm sorry, say again? They aren't the equations of motion there? Fair enough. Yeah, these are the conditions that I get. I'm saying equations of motion broadly in that all variations of the 10D action I would call an equation of motion, but you're right, these are the supersymmetry variations.
Right. So what about the actual equations of motion? How will then satisfy?
Yes. Yeah. Yeah.
What does DJ equal 0 imply for W3, 4, and 5?
Oh, that's a good question. Sorry, they're all 0 in that case. Everything is 0. Yeah. Yeah, so that's a good point. So here, in this case, Wi is 0 for all I in this condition. OK, so this guy, in the histories of string compactifications, these were some of the actually the very first string compactifications that were written down in the 1980s. People observed that this was true. Because this was such an easy solution to write down, it had its own name. This is called the, quote, standard embedding. But it's clearly a very special choice. There are many other solutions for a Calabi-Yau background. I can choose gauge fields that do not satisfy this coupling to the spin connection of the base. They can be entirely arbitrary gauge fields, entirely arbitrary satisfying these equations. And we'll look at those broader solutions in just a second. OK, so this is just a quick overview of what we need for the gauge fields. Now what we're interested in is what kind of theories do we get from this compactification. So if we can find geometry that solves this background, what will we get? So of course, we're starting with the 10D Sugra-Plossier-Mills. And what we're going to end up with is some 4D n equals 1 chiral theory. Bring this up a bit. So we're interested in 4D n equals 1 chiral theory. And the question is, what can we say in general about such a theory? So the first observation is that the gauge theory, as James probably mentioned, in 10 dimensions is fixed. So in 10D, we can have gauge group G equals E8 cross E8, or SO32. Neither of those, well, those are pretty limited choices and extremely large gauge groups for doing interesting physics. So of course, we would be interested, can we choose non-trivial background vevs for the gauge fields, so A over Calabi-Yau, non-zero, such that we break some of this gauge symmetry down to perhaps more interesting subgroups of E8 cross E8 or SO32. And indeed, that can be done. It's precisely these non-trivial vevs for the gauge fields that are parameterizing what I've called the bundle. So here, bundle. This is just geometrically keeping track of non-trivial A mu on the Calabi-Yau background. What do I mean by keeping track? I mean that for any gauge field, you have gauge degrees of freedom at each point in the space. This is simply tracking that gauge degree of freedom over each point. So the bundle, if you have a space X, the bundle, a fiber bundle, keeps track of some information, whatever you want, tangent spaces, wind speed, temperature, in this case, gauge degrees of freedom, over each point. So if you have, for example, an SUN gauge theory, this is an n-dimensional fiber at each point over your compact space. OK, and the bundle I'm denoting V, which can be projected onto that manifold X. OK, so we begin with the 10D gauge theory. We turn on non-trivial background gauge fields on the manifold. And what you're going to end up with in 4D is G, which is an H, which is a subgroup of, for example, E8 cross E8 or SO32. And in particular, we're going to look at subgroup structure. So let's say inside E8, we want to look at subgroup structure of the cross form G cross H. Here, this guy will be the 4D gauge symmetry, and this will be the non-trivial vevs. So you'll break some subgroup and preserve some subgroup in 4D. All right, how about the field content of this theory? What can we say there? Well, we can consider in vacuum, obviously, the degrees of freedom that we have to start with from 10D are the metric. So we can consider perturbations around a background metric. And the 10D gauge field, which we're dimensionally reducing as well, A mu plus delta A mu. And what we want to know is, for which fluctuations of the metric in the gauge field will we still preserve these equations, these in the condition for the Calabi-Yau. So there's one, this can be done for either the metric or the gauge field. I'm going to do the easiest one just to illustrate. The very easiest one, let's look at, for example, this equation of motion. A bar, B bar is 0. And let's look at what happens when we fluctuate that. If you plug in a fluctuation of this type, so A goes to A plus delta A, what are you going to have? Well, clearly, you end up with a condition which looks like the covariant derivative, gauge covariant derivative, acting on the fluctuated connection has to be 0. This is just saying you start with a holomorphic thing, you fluctuate it. It better be the case that the fluctuations stay 0. So this means that d bar of delta A is 0. This is called the statement that the form delta A, the one form, is closed, and closed with respect to covariant derivative, gauge covariant. How about what happens if I look at exact things? So note, as is normal in gauge theory, if A goes to A plus D of something, d phi, this is what we refer to as pure gauge. So this doesn't change the physics. So what we want to count are the number of d bar closed fluctuations that are not exact. This gets a name. So you count fluctuations d bar closed modulo exact. What do I mean by exact? I mean d of something. Mod d of stuff. This is exact. This gets a name. This is called cohomology. In this case, bundle-valued cohomology. And we denote that. Here I'm counting one forms because I'm looking at perturbations of the gauge field. This would be written as H1 over some space X of some bundle V. So this notation just means I'm going to count forms that are carrying a particular index. So here I would have A mu. This is the space-time index. And I've omitted it thus far, but I would have some gauge index as well for the Yang-Mills theory. This V is keeping track of this guy. The X is keeping track of what space we're in. And the one form here is telling me how many of these indices I have. In general, people write HI X phi. These are I forms, so scalars, one forms, two forms, et cetera, over the space. OK, so the types of fluctuations that you're going to have around the vacuum are going to be things that obey the equations of motion. We can say that a little bit more precisely about how that actually gets related to 4D fields. So let's look at this a bit more explicitly. Heard that the real ninjas can actually do the board cleaning and be squeegeeing with one hand and writing with the other. That would be pretty cool. I clearly am not a ninja yet. Okay, good enough. So let's make this more explicit in one case. So in terms of matter, 10D, we have only a gauge field A mu. This is valued. Let me just explicitly do this for the E8 theory. I'm going to ignore one E8 factor just for simplicity. This is a gauge field. This is in the adjoint of E8. So this is the 248 rep of E8. This is the only matter degree of freedom we have in the 10D theory. So when we dimensionally reduce, we consider E8 going to G cross H, getting broken. Remember, these are the vevs of the gauge fields over the Calabi-Yau. And what that's saying is we can consider some subgroup. So just for illustration purposes, if E8 gets broken, it has an SU5 cross SU5 subgroup. If I turn on gauge field vevs in this SU5, I'll leave the other SU5 unbroken. So what I want to consider is how does this representation of the 248 decompose under such a product group? And that's easy to write down. So the 248 goes to the following representations of SU5, SU5. There's a 124, a 5 10 bar, 5 bar 10, 10 5, 10 bar 5 bar, and a 24 1. Okay. So all I'm making the observation with this is that if you want to say what type of representations can arise in your lower dimensional Yang-Mills theory, that is completely fixed by the 10D theory. So this is not up for grabs. You start with, in our case, E8. You say, I've turned on vevs in this guy. These are the types of representations of SU5 that I can be left with in 4 dimensions. This is what could arise. This is not what necessarily does arise. So possible, but may not happen. How do I see if this actually, which of these reps really does turn up in the 4D theory? So this is possible matter, charged matter. And the observation here is highly constrained. How do I see what really happens for a given compactification? Well, we have to do this fluctuation that I just did a moment ago a little bit more precisely. So over the Calabi-Yau background, on the Calabi-Yau, I consider a fluctuation of my gauge field, which takes the following form. Write that one down too. Put that guy up. Okay. So here's a big mess. What are the ingredients? Delta C is a fluctuation of the matter field in which I've pulled out the 4D dependence. So this guy is going to be the 4D matter field. What are the indices? I here will be a flavor index. This is just the multiplicity of how many such matter fields I'm going to have. X, this is going to be what we call a G rep. So this is a G index for the gauge index over the 4D Yang-Mills theory. Here, this guy is a Calabi-Yau space-time index. And alpha, this will be the H index, i.e. the gauge field over the commutant of G within E8. Does that make sense? So here T is a generator of the product group that we're considering, G cross H. And the interesting part here is omega I A bar alpha. Again, multiplicity index, flavor, and spacetime. This guy is a basis of closed one forms that do what we want for the equations of motion. So the way we phrase that is a basis of, quote, harmonic forms. These are just things that satisfy d bar omega is 0 and star d bar omega is 0. These guys are guaranteed to solve the twisted Dirac operator being 0 that we have for our vacuum solution. And if I plug in such a fluctuation, this will be a flat direction of the potential. So a flat direction from the point of view of both the 4D and 10D theories. So this is a massless degree of freedom, gauge charged in this case, in the 4D theory. And the 1 forms here will guarantee that we have a solution. They will parameterize the solution over the compact space. So here, the index I, this is counting the number of such forms, i.e. the number of matter fields. Multiplicity of matter fields. And of course, since I'm just counting d-bar closed forms that have some gauge index, this is a, quote, cohomology calculation. This is just a geometry question. So I can go away and I can say, how many forms do I have of this type over this space? And that will tell me the multiplicity of the matter. For many solutions, these are going to give you Yang-Mills theories that are very weird. So you could have hundreds of, 5s of SU5 in your SU5 gauge theory. You could have no matter at all. Even though this is allowed by the decomposition of the 248, it may be that there actually are no 1 forms allowed for the space that we've chosen. So this is a highly constrained bit of spectra, and of course it would be interesting to see what you can get. This is the story for the gauge fields. Let me just mention briefly that I haven't talked about the metric fluctuations, though they're pretty much the same story without the gauge degrees of freedom. Again, they're going to be parameterized by harmonic forms that tell you about how the metric can fluctuate, closed but not exact forms. And metric fluctuations, these guys will give you 4D scalars, obviously, no gauge indices. So the metric fluctuations come in 2 types. The so-called complex structure fluctuations. These can be parameterized in terms of the data that we had before in real indices. The 2 form, this is this guy. J, A to 0. This object is a matrix, squares to -1, hence the name complex structure. This is the object that we are guaranteed with the vanishing of those 2 torsion classes gave us a complex manifold. And, quote, the Kähler structure. And this guy came from dj being 0. The fluctuations here, this is Gij going like this one. This is the Kähler form. And in this case, we can write the metric, d squared. Viewing this as a 2 form, this is another description of the same object in complex coordinates. These fluctuations are also counted by, quote, cohomology. In this case, these are 1 forms that live in the tangent bundle to the space, same notation, closed but not exact 1 forms. And here, these are 1 forms that live in the cotangent bundle to the space. Put those in boxes. I am not doing a good job of telling you where these came from. This is actually, it's kind of an involved story to write down the metric and show that these are the only 2 independent things you can do in the Calabi-Yau case. That's an important calculation, but it's one that's very old and it's very easy to look up in a lot of good literature. And I want to spend time today talking about stuff that's a bit more interesting or new. So let me just give you where you can see that this is the whole story. Set of references. So to see the details, see, for example, Philip Candelas has a lovely set of lecture notes, which as far as I know, weirdly, are not on the archive. These are sort of ancestral lecture notes on complex geometry that are beautifully written. If you don't have them, somehow, like most people end up with them, somehow someone gives them to you. If you don't have them, send me an email and I will send them to you. They're quite cool, well written. You can also see a lot of this, of course, in Green-Schwarz-Witten, Volume 2. And for a more modern take on the same fluctuations in the context of SU3 structure, Guerreri et al., FTH 02110102. Okay, so that's just, those are references for how do you see how to do the fluctuations of metrics in Calabi-Yaus. the gauge fields we just did. What I want to spend time on, rather than going through those details now, is how do you characterize what types of theories you really get in one of these compactifications? What can you say in general about the structure of the manifolds, the Calabi-Yau manifolds in this case, and the gauge fields over them? How do those degrees of freedom talk to each other, and what can you say about the effective physics? So let me just summarize briefly, and then we'll move on. So what we've observed so far is the 4D heterotic theory that we get from this compactification will end up with a bunch of massless scalars in 4D. These will be counted by multiplicity that is determined by the geometry. We will have the complex structure degrees of freedom, the Kähler degrees of freedom. Also, I didn't do it explicitly, but there'll be fluctuations of the gauge field for which the gauge index is entirely in the internal directions of the space. So these will be bundle moduli, so-called. These are denoted as follows here. So these are bundle scalars. This is for the scalars, and there'll be charged matter. These are counted by some one forms H1 XV. A bit of notation. Would people use this notation to say the manifold and the gauge indices that I'm interested in on the forms? Obviously, different representations of the gauge bundle will appear, and people change what they write for this guy. So this is usually denoted for the bundle of the fundamental rep. And then there'll be other notation here. For example, this is the adjoint. How this guy is written. We'll come back to this in a minute, but again, this is just the data that you see in the second part of this bracket is just telling you what representation of the gauge group this is valued. Okay, so the charge matter is counted by these guys, and we have, of course, some gauge group G, which is the subgroup. I'm going to focus on the E8 case, but we could do this for SO32 as well. All right, so obviously there's a bunch of questions we want to ask. First question you might ask is why, I wrote this all down, obviously, for the sake of simplicity and ease in the Calabi-Yau case. Based on what James said last time, why are we even interested in the Calabi-Yau case? You could ask that. And the answer is because in the case of this background, after nearly 30 years of people thinking about string compactifications, we are just barely getting the technology to start to fully extract the effective physics from this kind of process. Turns out that the geometry that we need to analyze in order to really be able to say anything about the physics is pretty horrible, and the concerted effort of 30 years of physics and mathematics is finally giving us tools where we can get somewhere meaningful. Also, when I was an undergrad, I took a class in differential equations, and the professor was explaining our focus on linear versus nonlinear differential equations. It's like dividing the universe into bananas and non-bananas. It's a true designation, but not terribly meaningful. Of course, there's the lamppost effect here. We know how to actually solve stuff in Calabi-Yau, so we can go the furthest, and thus it may be the most interesting to us. But many of these tools we can try and apply in other settings as well. Okay, so we want to ask questions about how to bound these theories, and let's begin by asking what geometries we actually have in play. So the multiplicities here for the matter fields obviously matter to us. What can we say about the types of geometric backgrounds that we actually have? I should say, by the way, that most of what I've just said is pretty readily found in various review articles or textbooks on string compactifications. Where I'm about to go with what's possible with geometry is not so readily available, and that's why I want to focus on that. Okay. So, questions. If this was a highly constrained geometric problem, life would be easy, right? So if there's like one Calabi-Yau, we write down the theory, we see is it a theory we're interested in or not. We go have tea, it's great, we don't care. Unfortunately, we want to ask how many CY backgrounds are there? And we will see whether this is an interesting question or not. Can we build them? So can we actually calculate everything we need in order to work out the effective physics? And of course, we have to ask the same question about gauge fields on X. So I'm going to begin with the manifolds. And you will find when people write down Calabi-Yaus in literature, they all write down a vast zoo of different constructions. It can seem a little bit overwhelming when you first look at how people are writing these down, but they're basically grouped into three main ways of building geometry. And it's surprisingly simple how these are actually built. So there are three main, let's start with X, and there are going to be three approaches that people use to building Calabi-Yaus. Okay. Basically, almost all manifolds that are known are going to be built using one of the three that I'm about to describe. The first is the so-called algebraic varieties. This just means we write down polynomial equations in a space to try and define them. So that's pretty easy. The idea is we want to write down X Calabi-Yau inside some ambient space, which I'm going to refer to as A easy. You want to write down a super easy ambient space, you want to write down some equations in it, and you want to get a Calabi-Yau solution. So this will look like a solution to a set of polynomial equations, P1 up through Pn, which are polynomial. Pi will be polynomial in the coordinates of A. And here we're going to see that the topological data, so we'll come back to this in just a second, but the topological data, i.e. the things that determine the Calabi-Yau, these will be invariant under small fluctuations of these equations. So you would hope that if you change the equations just a little bit, you fluctuate how you're defining them, you're not drastically changing the manifold. And so we'll be able to build families of manifolds based on writing explicit equations pretty manifestly. So examples. One that I imagine most students who studied a little string theory somewhere have seen is, of course, the quintic. That's the first one you write down. This you take as a easy space P4, and you write down a degree 5 equation, for example, x naught to the fifth. Sorry, I'm getting feedback here. Let's see if that's better. Any idea why I'm buzzing? Okay, as long as it's not bugging you guys, I'm cool. But okay. We're going to come back to this explicitly in just a second, but the basic idea, just write down a polynomial equation, hope it defines the manifold for you. The next approach is by so-called fibrations. And what's the idea here? We want to fiber one simple geometry over another. And this is sort of building the manifold like you were building it out of Legos. You take your favorite building blocks and you try and clip them together in some easy way. Mathematically, a fibration, the definition, is a continuous mapping pi, which takes, say, the space you're interested in into some other. The fibration, we say a total space maps onto something called, quote, B, the base. And this continuous mapping is a fibration such that for almost all points, we'll say for most points, if I pick a point in the target space B, and I look at the inverse image of that point, or rather any 2 points, say B, B prime, So pick 2 points in base. If you look at the inverse image, what you see here is that the inverse image of any 2 points in this space is, quote, the same. What do I mean by the same? This is called homotopic. And we refer to pi inverse of any given point as the fiber, and B is the base. This may be obvious to you what this means, but if you're just saying this for the first time, likely not. So this looks formal, but is actually quite easy. The idea, again, is you're just going to stack one space over another. So let's do some easy fibrations. So EG, let's take the simplest one possible. R2 is a R1 fibration over R. That's about as easy as it gets. So here's R2. Pick any given point in the x-axis, and above it, you have another copy of R. So here, in this case, I have x and y. X-axis would be my base B. Y-axis would be the, quote, fiber of this fibration. Just saying, pick any given point. There's a projection down to the base. That's this map here. So I have a unique point in the x-axis given any point in the plane. And if I pick any point in the x-axis, if I look at the pre-image or the inverse image of the projection under that, then I will find a copy of the fiber, in this case also R. Okay, that's a little bit too boring, so let's do, that was EG1, let's do EG2. What if I have some non-trivial shape to my space? Another simple example, the cylinder. This is a copy of a line. In this case, this is an R fiber over S1. That's also pretty easy. So pick any point in S1, look at the image above it, you have a copy of the real line, and you're good. More non-trivially, 3, we can ask, is this the only way that we could fiber a real line over the circle? And of course, there is one other choice, which is going to tax my artistic abilities to draw, and that's the Mobius strip. Yeah, it's not happening. You get the idea. Mobius strip. Apologies for the bad art. In the Mobius strip, what happens? Well, at each point in the circle that's going around the Mobius strip, you have an S1. Obviously, I have an R fiber over each point. So if I look at each point on that circle, I have a line above it. But what's happening is that as I move around this circle, there's a non-trivial twist that R can undergo because of the global topology of that S1. In case you're saying, why do I care about this geometry? This is a statement, albeit a little weird, that if we were doing U1 gauge theory, you can think about this as, I want to do U1 gauge theory on a 1D space, S1. There are only 2 ways to build U1 gauge fields on S1. You can do it trivially, that's this guy, or there's a non-trivial choice. And in fact, these are the only 2 ways to build fibrations, R fibrations, or in fact, we can make this C in the case of a U1 gauge field. Line fibrations over S1 come in one of these 2 flavors. So this would constrain gauge theories, and you'll see where we're going to go with this in the Calabi-Yau case when we come to bundles. If you have a non-trivial space, like a Calabi-Yau that has non-trivial boundary conditions, as you twist various degrees of freedom over them, there'll be very constraints about not every gauge theory can be realized on every space. So this is a simple example of fibrations, and I've gotten a little ahead of myself. What I've actually described so far for these examples is all, in fact, bundles. So these would be R bundles over the various spaces. What's the difference between a bundle and a fibration? It looks basically the same. The answer here for a fibration is that these pre-images, so the fibers, have to look the same for almost all points in the case of a fibration. And in the case of a bundle, it has to be true for literally every point. So here, literally every fiber looks the same. In the case of some fibrations, though, you can have something weird. So let me shift up the board and show you what that looks like. So this is an aside. Bundle. All fibers are the same. Fibration. Some fibers can degenerate. So instead of having, this is my space, all the fibers are going to look the same, and at some point I can have a weird squiggly fiber that looks different than the others, as long as that happens non-generically. So the statement in my definition, which I just pushed up there, was that almost all fibers look the same in the case of the fibration. The statement here is that for higher codimension in the base. So as long as this doesn't happen generically over points in the base, you're good. Okay, so these are our easy examples of fibrations that we've done so far. Obviously, every fibration is, quote, trivial, i.e. it looks just like a product space, like my first example. So fibrations locally look like fiber times space. And in the case of both the cylinder and R2, they were literally those products. But globally, they can have non-trivial twist. So on the example of the Mobius strip, this twists non-trivially. Every fibration over either Rn or Cn is trivial. Everything factors as this product. You need to have compact spaces like S1 or Calabi-Yau in order to have non-trivial structure in terms of what you can write down for the fibers. Okay, and now the third approach for building manifolds. So third construction is, quote, manifold surgery. And the idea is to start with some easy space. Let's call it X easy. And we want to locally patch in another easy space. Let's call it Y easy. And we get some new space at the end, X prime. You've already seen this procedure being described in other lecture courses in this school. For example, the process of blowing up a geometry is one example of this. So in the case of blow-ups, you can start with some space, you can pick a point, and you're going to replace that point, either blowing up, resolving, for example, is another process like this you may have heard of. And at that point, you can replace it with other things. So for example, in the blow-up procedure, you can pick a point and replace it with an S2. If you do that, you're just changing the global topology of the space. You pick any given point, you remove the point that we were considering, you glue in a sphere. You could do that over a line as well in the space. So at various higher codimensional points, you just pick regions of the geometry, you cut them out, and you stick in a new bit of geometry, and that gives you a different space. In the case of Calabi-Yau's, where this gets used a lot, and this was already used in some of the lectures that you've heard this week, frequently the way that this is done is you start with a singular Calabi-Yau. You go to the singularities and you say, those are gross, I don't like them, I want a smooth manifold. And once you find the singularities, you can then replace them with simple spaces like this S2, and then end up with a smooth. So end up with smooth Calabi-Yau's. And this is a nice way, given one space. So if you have one Calabi-Yau that you know about, you can consider all the ways you can make it singular. You can see how many different ways you could fix those singularities by gluing things in. And then you can see whether you get new geometry at the end. OK. We're going to begin with just a quick illustration of the first approach, the algebraic approach, because that's, of course, the easiest. And I want to illustrate for you where this gets interesting and complicated fast. So these are the sort of three approaches: algebraic, fibrations, or blow up or resolve various spaces to make different ones. So let's start with one. Start with algebraic approach. What do we get there? So remember there, the game was we had an easy ambient space, and we want to write down some equations. what is the easiest space that we can think of? You can start really easy. Rn, thank you. That's my favorite easy space too. So we can start with Rn, that's pretty easy. But remember that we said in the case of Stromender solutions, we were interested in complex manifolds. So what's a complex version that's really simple? We could start with Cn. Maybe. Cn is a pretty good choice, but the problem with Cn is that we're interested in compact manifolds, and Cn is non-compact. So you could still write down, equations that could give you something compact inside Cn. That's possible. But it would be even easier if we could start with a version of Cn that was compact and write down equations in that, and then life would be even easier still. We'd have definitely complex manifolds that are compact in the game. So how do I make an easy version of Cn that's compact? The idea is to compactify Cn, and this gets a name. This is called compact projective space, or complex projective space, CPN, frequently abbreviated to just Pn. And the idea is take a bunch of complex coordinates, z0 up to zn, like you would for Cn, and try and get rid of the ability to go to infinity. So how do you do that? Well, you just want to mod out by a scale. So you're going to introduce any two points in the space which differ by any overall scale you're going to call the same point. So as you try and head out to infinity in any direction of the space, you're just going to wrap it back around and say it's the same space, same point. Is there a question back there? No? OK. So take your coordinates. This process is called projectivizing the coordinates, introducing this scale for lambda not 0. By the way, I should say. So example, the simplest one, if I take P1, one complex dimensional projective space, what's the idea here? I have two coordinates, z0, z1, related by scale. That gives me one complex dimensional space. And what space do I get? This is actually just as a real manifold S2. So if I look at the two-sphere, here, the rule, obviously, since lambda is not 0, is that z1 equals z0 equals z1 equals 0 is not a point in the space. And you can view this just like a version of R2 in which you've taken infinity and wrapped it around to form the poles of the sphere. So again, just compactifying flat space in a very obvious way. That's projective space. We can say within projective space, could we write down an equation? And for those of you that have seen this kind of thing before, the answer is, of course, yes. We can write down things like the quintic and many cousins of it. Can we write down a simple equation in this compact version of Cn and see what we get? So we want to now build a Cy in Pn, for example. So we want to try, let's say, one holomorphic equation. So we want to define x via the 0 locus of some polynomial in my coordinates zi equals 0. And this gets written in notation that I've already used as Pn m, where this m is the degree of the poly in the z's. So this is a homogeneous polynomial of degree m. So z0 to the m, a0, a1, z0 to the m minus 1, z1, blah, 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 whole bunch of coefficients. Degree m polynomials in these z's equals 0. Does anybody spot why I need a homogeneous equation in this setup? Yeah.
Otherwise it would make sense on CPN.
Yep. The scale messes things up for you, right? So I shifted, if you have an inhomogeneous equation, if all the coordinates scale differently, that 0 locus wouldn't even be well defined. So this better be a homogeneous equation if you want to have a sensible solution set to it. So you can write down an equation of that type. We want to write down holomorphic equations because we're interested in preserving the fact that the solution is a complex manifold. And nicely enough, with this embedding, we also have a process, so we're interested in the metric and whether this is a Calabi-Yau space. Pn has a natural metric that exists on it. It's the so-called Fubini-Studi metric. And this Fubini-Studi metric looks like GA B bar, D bar B, log of various coordinates up to Zn squared. So we can now ask, if you take the natural metric on Pn and you restrict it to a polynomial hypersurface of this type, under what conditions can you have a Calabi-Yau solution? So let's restrict GPn to G on the P equals 0 locus and ask, what do we have? Let's define, let me write this as G on X. And here X will be defined as the polynomial equals 0 solution. If you do this, in general, this will never be Ricci flat. So you remember, you want a Ricci flat metric on the Calabi-Yau. But you can do this restriction, and you can say, just taking the restricted metric, since this is a submanifold of my total CPn, what do I have? And you can show I could be evil and say homework exercise. This is actually not that easy as a homework exercise, so only do this if you're feeling macho. You can show as a homework exercise that if you take the Fubini-Studi metric and you restrict to scalar curvature, what you get is the following. Sorry, I think I called this degree M. Yep. True confession, I didn't realize exactly how difficult this was, and I gave this as a homework problem to some undergrads like a semester ago, and they were not happy with me. So apologies, but you can do this. It's a big GR problem for submanifolds in a complex space. You can do this restriction, and what you find is that it has a really simple form. You get this prefactor of the Fubini-Studi metric itself restricted to the hypersurface, plus a bunch of total derivatives. OK, why is that interesting? Well, what this is saying is that if you have a very particular relationship between the degree of the equation you're writing down and the ambient space that you wrote it down in, the projective space that it's living in, namely, you can see if m is equal to n plus 1, then it is clear the trace of r is 0 over the Calabi-Yau. And this is equivalent to the statement that C1 of x is 0. And if you recall from James's lecture, the condition that you have Kähler and vanishing first string class, i.e. vanishing trace of curvature, this is equivalent to the statement that you have a Calabi-Yau manifold. So it is, in fact, quite easy to write down equations in a simple space like projective space, which give you a Calabi-Yau solution. Again, I do not, through this trick of restricting an easy metric onto a subspace, I do not have the metric I want. So this is just showing that the first string class is 0. This is not the Ricci flat metric. No Ricci flat metrics are known explicitly for any non-trivial Calabi-Yau manifold. And this is a major bummer. If we had complete control of that metric, we could do like we do in any GR or cosmology course. You just write down the metric, you analyze the theory. We would have complete calculational control over everything we wanted. Unfortunately, the very best we have at the moment are some numeric approximations to these Calabi-Yau metrics. But thanks to a theorem by Yau, we can guarantee that such a thing exists, and we can write down the conditions for it to exist very simply in a space like this. OK, so clearly, the example that you've seen before satisfies this condition that I've just written down, a degree 5 equation in CP4. This is a 4-dimensional complex space. One equation, that gets you down to 3 complex dimensional space. If it's a degree 5 equation in a 4-dimensional space, it satisfies this condition. Therefore, it is a Calabi-Yau. Now, it is obvious that that is in fact not the only one, and I'll just finish this and then we'll pause and have like a regrouping before we dive into the second lecture of the morning. It's clear this is not the only one, so what else could we write down? So, for example, we could write down more than one equation. So imagine that I start with P5, that's a 5 complex dimensional space. So to get a threefold, I need 2 equations. And it turns out that you can repeat this analysis for a space like that, and you can find that the degrees just add up. So you can see that something that looks like this, 3, 3. So this is polynomial 1 of degree 3, and polynomial 2 equals 0 of degree 3. That's what this 2-column notation inside the brackets is. 2 degree 3 equations in P5. This will satisfy that the sum of the degrees, sum of degree equals n plus 1. Here, 3 plus 3 is 6, 1 more than 5. That will give you a Calabi-Yau. Likewise, I could write down similarly a different partition of 6 in this case, P5, 4, 2. That guy will also give me a Calabi-Yau. And you can keep going. So P6, 2, 2, 3, etc. So it seems clear that I could just go on forever, right? I could just keep making a bigger and bigger complex space. You add more and more equations. And in principle, one could generate an infinite number of Calabi-Yaus this way. You can see right away, though, that that's not going to happen. So what happens if I write down this guy? So 5-dimensional complex space, 2 equations, 1 of degree 5, 1 linear. Anyone spot what happens to that? So I have a linear A0, Z0, blah, 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 in Z5 equals 0, and some polynomial of degree 5 in the Z's equals 0. Yeah?
The one linear equation just restricts you back to P4 and
Exactly. So linears are easy to solve, right? So linears you could just solve, as he just said, for one of these coordinates, and that drops you in the number of projective coordinates you have down by 1. So this would actually remove 1z from the game. That takes P5 to P4, and then we are left with a quintic equation. So as he said, this is just equal to P4, 5. So in fact, this is not an infinite family at all. This is a very short game to play. There is, beyond what I've already written on the board, in fact, only one more independent manifold you can write down. You can get up to P7, 2, 2, 2, 2, and then you stop. Why is that? Well, here I need a partition of 8 into 4 equations, and I can't use linears. If you tried to go up one further, if you tried to have P8, you need a partition of 9 into 5 things, none of which is a 1, and you can't do that. So it turns out that you will actually stop at this point, and these are the only manifolds that you can build in a single projective space of this type. However, that, of course, is not the whole story. So there's not just 5 Calabi-Yaus. That would be nice if that was the case. We can say, well, can we generalize this type of construction to other, in easy ways, to write down other algebraic Calabi-Yaus? And the answer is, of course, we can. So let me write down 2 easy generalizations, and then I'll pause just very quickly. Okay, so other generalizations. You can take A easy and start multiplying them together. A easy 1 times A easy 2. And then write down polynomials equal 0 in that space. That's pretty easy. So an analog of that would be to write, in terms of these matrices, something like P1, P3. And here the notation gets written as 2, 4. What does this mean? This is a Calabi-Yau hypersurface in the ambient space. A is P1 times P3. And the column here gives me the multi-degree of my homogeneous equation, one polynomial of degree 2, 4. Let's call these coordinates x and these y. So this would look like something like x naught squared, z naught to the 4th plus other terms. And that equation equals 0. You can show, again, using the Fubini study metrics on the two product ambient spaces, restricting. You can show the whole Calabi-Yau story goes through as before. One other generalization that's very easy is you can change the way you made the compact space. So I made a compact space by saying that the coordinates z0 to zn, as I try to go to infinity, I want to re-identify points to wrap back around. Just like taking a line and taking the real line, you take the points at infinity and you glue them together to make the circle. Same idea. I want to identify points along these rays, these scales. Who said that all the coordinates had to scale in the same way? So another easy generalization, you could try instead something like taking, for example, z0, z1, z2, and having them scale with different values of lambda. And this will also produce for you a compact space. This is called a weighted projective space. So this, if I had just 3 coordinates, homogeneous coordinates, this would be CP2 in the normal case. Now that I've changed the scales, this is denoted as P1, 2, 3, because I have 3 different scales. So first coordinate scales as 1, second scales as a 2, third coordinate scales as a 3. Called weighted projective space. Projective space. And here, the coordinates, the sum of those weights equals the degree of the polynomial. And this has to add up just like we had before. So for example, Calabi-Yau can be written as, I can use 1, 2, 3, 6 as an example. Here, if I sum the degrees, this will satisfy the Calabi-Yau condition. And here I've written a 2 complex dimensional space because I have 3 coordinates related by 1 scale, and 1 equation. This would be a Calabi-Yau one-fold as written. Okay, so far so good. So those are the algebraic constructions, and we should pause here because I'm going over time. Any questions on this bit before we dive into part number 2?
Are all Calabi-Yau manifolds algebraic varieties?
No, not necessarily.
No.
So there are known, for Calabi-Yau two-folds, there are non-algebraic K3 surfaces that are known. For Calabi-Yau three-folds, to my knowledge, that's an open question. I don't know of any non-algebraic. Actually, sorry, for Calabi-Yau three-folds, I think the answer is actually that yeah, I think actually every Calabi-Yau threefold will be algebraic, now that I think about it. So I think this actually follows from, so this, certainly the statement that I know to be true is that solutions, algebraic solutions to the Strominger system are definitely Calabi-Yau. But the reverse statement, I certainly don't know of any non-algebraic threefolds. There are some weird ways to not necessarily be able to realize these by simple equations. But that's an open question as far as I know. Other questions?
Okay, if there are no other questions, let's thank Lara again.